So how to solve for input impedance? I have a couple of problems down here below, and we're gonna solve them with a quick method, and we could see how the absence of different resistors and maybe RB or in the base and the emitter collector could change these formulas. So without further ado, let's get started. Let's focus on this first BJT, BJTA as I denoted, and what's the first thing that we look at, right? When we're determining impedance, the first thing we look at is the AC signal. And the reason we look at this AC signal is because it also implicates a current, right? In this particular BJT, we see that this AC signal is right at the base. This voltage source implies this current in this direction. And it goes down to the emitter. And typically the input goes only from the base or to the emitter, or the emitter to the base. So the second thing we also have to pay attention to is the base and emitter. So as we follow this path, this current path, right, we see that we start from ground and we go up until we touch the resistance at the base, this RB. So when we're writing this input impedance, typically denoted as Rn or Rin, we add or we implement this resistance. And this resistance remains unchanged. There's nothing special about it. Great. We just keep moving forward. So as we keep moving forward, we finally hit the transistor. And wait, we need to remember there's something special in this case. We need to remember that right here at this leg where the BJT has its arrow changing to the emitter, there's actually a resistance, and this resistance is typically denoted as R pi. And R pi is something we typically find in the DC analysis before we get to the input impedance or output impedance. So yeah, so as we get to R pi, we simply input it within the input impedance, right? We have R pi now. Now, as we keep going, we realize that we pass the base and we finally get to the emitter. And this emitter has a resistance of Re. And the only special change in BJTs when we're finding input impedance is that this emitter resistance has to have or has to be multiplied by a constant of 1 plus beta. Another constant that's typically given to you, or you're asked, no, this constant's typically given to you. So after this resistance, we go straight to ground, which means that we're done. We finish with this input impedance. And yeah, there's nothing so special about it other than the resistance at Re, which we have to multiply by the constant. So let's do another problem quickly and then go into other special cases. So we focus at this BJT, we focus on BJT B, which I denoted here. This is another NPN, right, where we have our emitter right here, we have our collector, and we have our base. Now, the only difference between this BJT and the other one is that this resistance RB is not in series with this voltage source. Instead, it's in parallel with it, right? So what does this change? Well, like I said, we're focusing on the base and the emitter, right? So let's redraw this real quickly so I can make this easy to understand, right? Where we have Vn, which goes to a resistor Rb, right? And now I'm gonna model this part, right? This part here, let's remember we have a resistor right here called R pi. So let's implement this resistance. And let's implement Re2. So we have Re and R pi, right? And to color code this, right, the green side on the left and the green side on the right are the equivalent of each other. So what we notice when we look at this circuit to the right is that RB And R pi and RE, they're in parallel. And we know what to do when things are in parallel, right? So what we see is that RB is in parallel with the accumulation of R pi plus RE. But what do we do with RE? Like I said before, right? If we look back to the previous problem, this is where we multiply by the constant 1 plus beta. And that's exactly what we're going to do here. So 1 plus beta. And this right here is our entire input impedance, right? To reiterate, let's think of it like this, right? We're going to have a current that goes through the voltage source. This current's going to reach this point, and then it's going to split. It's going to split downwards, which means we're going to have RB, right? I'm going to write it down here again. We're going to have RB. Now, as we go to the right, we're going to hit R pi. And this R pi is in parallel, right? It's in parallel to RB. And this R pi is also in series with RE, which we also hit. And RE is multiplied by the constant 1 plus beta, right? So hopefully that helped a little more. But yeah, this is how we get the input impedance for this particular BJT. So yeah, let's move to another problem. So what happens when this voltage source or the AC input, instead of being in the base, is now in the emitter? Well, this is where we start flipping some of the logic that we were previously doing, right? Like I said, and one of the important points is that we want to focus on the implied current that this input signal brings, right? And the current looks something like this. So what we see is that as we go up, right, we hit resistor RE. Now the question then becomes, what do? Do we multiply RE plus the constant? And the answer is no. And the reason the answer is no is because this resistor RE right here is in series with this input source. So anytime the input source and the resistance are in series or even in parallel, they are not multiplied by this constant. So now that we know that, as we continue, we hit this R pi, right? We can't forget this R pi. So now that we know that, right, let me move this to the left a little more to have some space, right? We see that we get to this point, R pi, right? Which means that this R pi, as we keep going, is actually in series with this resistance in the base resistor RB, right? So as we keep going, we have R pi, and it's in series with the resistance in the base. So what do we do now? Well, we also have to multiply this section now by a constant. What constant is that going to be? Well, simply, it's going to be the inverse of the previous constant. So we're going to have a 1 divided by 1 plus beta. And this formula as a whole is going to determine our entire input impedance in this BJT at C. So hopefully that wasn't too confusing. I'm going to try to go with a slightly more confusing problem. And what we're going to explore in this next problem right here is what happens when we do this with a PNP, and instead of starting with our circuit already designed in AC analysis, we are given the circuit as it would be given in the problem. So let's look closely here. We're being asked to solve for the input impedance at this area right here. And this area starts right here at this blue node. So let's redraw this in AC analysis, right? And how do we do that? Well, when we're redrawing an AC analysis, everything that goes to VCC right here, anything that touches VCC, VCC is going to be converted to ground, right? So let's get rid of this VCC and imagine this as ground. So what's next? So let's redraw this in a way that makes it easier for us to understand. I'm not changing anything of the circuit right now or any conceptual aspect of it. I'm just moving this to the right, and I'm gonna flip this over and move this to the bottom. All we've done so far is make VCC go to ground, right? And we also have to realize that since we're being asked to solve for the input impedance at this area where Rn is the blue arrow, this is where we're going to start. So this part right here is not going to matter to us. And as we follow the current path, right, which the current path would go this way, because we have a PNP. This is the emitter, right? Let's not forget that. So as we follow the current this way, the current is going to split down this way and down this way. So let's write this down. So we have Rn, right? What does Rn hit first? Well, as we start going to the right, Rn is going to hit R pi. We can't forget about R pi, right? We have R pi. So R pi is going to be in series with the emitter resistance, right? And this emitter resistance is going to be the accumulation of both of these. But this time they're not in series. What are they? Well, they're in parallel. We know what to do with things that are in parallel, right? Once we get to this point, we realize that these two right here, they're in parallel, right? And what this allows us to do is simply write them in parallel, right? RE is in parallel with R1. This time, the input source is at the base again, which means that when we're going to be applying the constant, it's going to be to the emitter, right? As we did with these problems right here, and as we did with this problem right here. So we're going to multiply this parallel resistance, the entire resistance in this side, plus 1 plus beta. And this equation right here determines our entire input impedance for this problem. So hopefully these were helpful to you. Like I mentioned before, if you don't have a resistor, an RE, or let's say you don't have a resistor in RE, you could simply just pretend it doesn't exist. Sometimes you can't make them go to 0 because these are in parallel, for example. So you just pretend it's not there, and it would just be R1, 1 plus beta, right? It is basically a problem we've already done. So yeah, hopefully this was helpful to you. I'll make more videos soon. Thank you for watching.